Given 50 milliliters of 0.2 molar acetic acid, what is the pH after adding 200 milliliters of 0.05 molar NaOH? Okay, so this is a weak acid, strong base titration question, and the question also gives us the Ka of acetic acid. Great. So I think what I'm first going to do is find the concentration of current OH minus that we have. And we know that the concentration of OH minus that we have is just going to be the concentration of NaOH since, it's just Na plus OH minus. So the concentration is going to be the same. Pretty self-explanatory. So that is 0.05 moles per liter. And we know moles, this big M is moles per liter. And if we want to find the number of moles of OH minus that we have, we can just multiply the concentration by how much liquid we're adding, which in this case is 200 milliliters. So, okay, I'm recording, good. So what we'll do is we'll do the number of OH minus moles is just equal to 0.05 moles per liter times, and in this case, it's 0.2 liters. 0.2 liters. And these two cancel out, giving us the number of OH minus moles that we have, 0.01 moles. Great. Now I'm going to try to solve for the number of acetic acid moles that we have. Acetic acid. Now, this is literally just the same as before. We are given the concentration, and we just have to multiply it by the liquid that we're adding, or the volume, sorry. I should say liquid. So 0.2 moles per liter times 0.05 liters. These two cancel out, giving us 0.01 moles. Okay, so why did I do this? Well, now we're going to go ahead and write the equation for what this reaction will look like. What will it look like when our weak acid reacts with our strong base? And it'll look something like this. CH3COOH plus OH minus. And this reaction is not at equilibrium. It's just one step. Becomes H2O plus CH3OO minus. Now, we have a weak acid reacting with a strong base. This results in water and also a strong conjugate base. So when the question asks for the pH, like if we go a step backwards, whenever something asks for a pH, it's asking us to solve for the concentration of hydrogen ions, protons. But that could also mean solving for the concentration of hydroxide ions, and then, as you can see later, getting the POH and then 14 minus that. And in this case, a strong conjugate base will produce hydroxide ions. It will produce hydroxide ions when reacting with water. So we want to find out how much strong conjugate base we're producing so that we can find how much hydroxide ions that is producing. And to do that, we can use this equation right here. So we have 0.01 moles of this acetic acid and 0.01 moles of this strong base, as like we saw for before. And notice how these are both the same quantities, which means I can be honest, I could have made this question more complex and like not make it equal, and this would have had more, but these two will react fully with each other. There is no limiting reactant, so they will both react fully with each other to be left with no moles. Whereas on the other side, 0.01 moles of water will be produced, and also the answer to the previous question I was asking, 0.01 moles of our strong conjugate base will be produced. Amazing. So we have that, and with that, we can solve for the concentration of the strong conjugate base. So CH3COO minus is equal to, we have 0.01 moles of this in a 250 milliliter solution, because we added 200 milliliters to a 50 milliliter solution. So 250 milliliters solution, which is just 0.25 liters. And this, let me pull out my calculator, 0.01 divided by 0.25 results in a 0.04 molar concentration of CH3COO minus. Now, what we can do is write the reaction I was talking about earlier, where a strong conjugate base reacts with water to produce hydroxide ions. We can write that reaction, but that reaction will come to an equilibrium point. It'll come to the equilibrium point. And we want to solve for the number of hydroxide ions this reaction produces at that equilibrium point. So how do we do that? We use an ice table. So I'm going to write the reaction first, CH3COO minus plus any strong conjugate base will react with water to produce hydroxide ions. So it will produce the CH3COOH plus OH plus. And intuitively, this reaction also makes sense for being at equilibrium because given this, we just wrote this reaction up here. So it kind of makes sense why it would be at equilibrium, why it would be shifting from left to right, and that would happen. But of course, there's an equilibrium point, and that's what we want to solve for. So the initial concentration, as we saw before, is 0.04 moles, 0, and then 0, 0, and then minus x. This honestly does not matter, it's just water. And then plus x, plus x. And so we get that 0.04 minus x, x, x. That's our equilibrium concentrations. Now, with this, the question gave us the Ka of acetic acid, which is very helpful right now. So we can write that expression. So 1.8 actually, no, I'm sorry. I messed that up. Yeah, sorry. We're given the Ka of acetic acid, but in this case, because we're working with a hydroxide ion, we need the Kb of acetic acid. So Ka is equal to 1.8 times 10 to the negative 5. We have the Ka of acetic acid, but not the Kb. So we need to solve for the Kb. And we know that any Ka times any Kb is equal to 1.0 times 10 to the negative 14. And so Kb, if we just put this in here and divide it by this, Kb is equal to, let me use my calculator, 5.6 times 10 to the negative 10. Great. So we use this and these values to solve for a value of x. So 5.6 times 10 to the negative 10 is equal to x squared, so x times x, over 0.04 minus x. Now, I could do a quadratic equation and make this really complicated, but the thing is, this is more than times 100 of this, which means whatever is kind of happening on our reactant side, this x is kind of negligible. So we can just get rid of it. Well, not make the x and x, but we can just yeet it out of here. So you get x squared over 0.04, which makes this a lot more simpler. We don't have to set up a quadratic equation and do our formula. And with this, we get an answer very similar to what we would have gotten before. So we get x is equal to 4.7 times 10 to the negative 6. Now, this isn't always our final answer. We need to go back in here and look. So the final concentration of hydroxide ions is just x. But keep in mind this. If these two values were not equal at the beginning of the question, say we had more strong base than weak acid, the moles were more, then we need to add in the concentration of this to this as well when calculating our pH, because at that point, we need to substitute it into this portion of the reaction, because we have more hydroxide ions left in our reaction. We have to take into account those will affect our pOH. But in this case, we just know that the pOH is equal to the negative log of our concentration of hydroxide ions, which is just x in this case, negative log of x. And the pOH in this case, if I pull out my calculator again, is 5.33. But the question is asking for the pH. And we know that the pOH plus the pH is equal to 14. So the pH is 8.67. All right, great. That's the solution. Lots of steps, but yeah, fun question.